through. I want to go through the Turing machine example of how we actually create a Turing machine that will recognize the language A to the M hashtag. You seem surprised.
What's that?
Seem surprised.
I know, because we did part of that.
What?
We did part of it last time.
Yeah. So I want to finish it. B to the M, A to the M. That was the same language we did last time, right?
Yeah.
Okay. So remember that there's the way to, when you create a Turing machine, the way to go through this is to first think about at a high level, what would you like to be doing here? Because the idea is that a Turing machine can do anything that you can do in pseudocode. We're not going to show that, just take my word. So let's talk about how would I create a Turing machine to do this? The two phases for this. One is you want to recognize if it's in the proper format. If it's not in the proper format, then screw it, we're done. The second thing you want to do is you want to do a validation testing on it that the condition is still here. And the condition that you're still doing on this one is that you have the same number of A's and B's. Okay? So Turing machines always start off they start off infinitely deep to the right, but they have nothing on the left. So the first thing we have to be able to do is we have to be able to denote whether we're starting with an A, where the starting condition is or not. So let's start off again. And for this one, we can actually, I think last time I had it greater than 1, but we'll make it greater than 0 here to mix things up from last class. So we have our start state there. If we see a space as our first character, that means our string is empty. And that's going to be a reject. That will take us to a reject state. Another option we could have is if the M's are empty, we could have 2 hashtags in a row. And so in that case, I know I should write this out, space goes to space, right? Another option that we could have from the beginning is if M is equal to 0, we could have 2 hashtags. Hashtag goes to hashtag, and that goes right. From there, we have to do another hashtag goes to hashtag right. And then if we see from there, space goes to space, space, which goes to space, which goes to right, then that's actually going to be an accept. And that's a special state where we have 2 hashtags and that's it. We have to put the final validate here that we see a space after our 2 hashtags, because it could be, if we didn't have that, it could be the case that we have hashtag, A, which of course wouldn't be allowed. I'm not going to show most of the rejects from here on. I'm going to say that if you don't see a connection that's coming out of there, just assume that connection's going to the reject, because I don't want us to spend time doing it. So now we've handled the special case where M is equal to 0. Let's talk about everything else. Everything else we need to validate that we're in the proper format. So the first thing we will see if we're in the proper format is an A. And we want to mark this A as a special character to show that denotes the beginning of everything. And so what we'll do here is we will say A, and that goes to the right, and it becomes A dot.
So on the other ones below that, why does space go to space and not right?
Oh, sorry, that's just, I got dyslexic and mixed them around.
Oh, okay.
Unless you did it that way.
It doesn't matter. Yeah, I mean, unless R and L are characters in there, which will never be the case.
Because it's going, like A is going to A at right, so it doesn't matter if A.
It doesn't matter. Yeah, it's just going to it's moving right and it's changing it to A. So
Unless you're the variable R.
right. In which case, you really want to be careful that it's there. But small mistakes like that, people write them different ways. There's not really formally. If you want to be super formal about it, then you have to be consistent about it the whole way.
So just to be sure, the operation there is you're replacing A with A dot and then moving to the next
right
unit in the list.
Right.
Okay.
Now, what does matter is that you have the A before the arrow And this, so you have the input before the arrow, the output after the arrow, and the direction after the arrow. So that's what will really matter. But interchanging those two, it's not a big deal. I think traditionally I do write it with the. I think I dyslexited it up on the first one and then carried that over. But I won't take off any points for that. In fact, I don't know anyone who would. Well, and that's not true. I do know someone who would. He's Ukrainian, as it happens.
You know those Ukrainian people.
And built like a tank. It's like, I mean, really, like, he was my office mate for years. Anyways, so we move right one character, and we mark it with an A. And we do that so we denote that this is the beginning of everything. So now what we're going to do is we're going to keep on, we want to make sure we're in this proper format. A. And so we'll keep on seeing A, and we will replace that with an A, and we'll go right. We're not marking any of these yet because we haven't gotten to that phase yet. Okay? Now what we want to do is eventually we'll see a hashtag. And when we see a hashtag, we're going to go right and replace it with another hashtag. Now, I want to point out something that
Mixed up direction and placement again.
man, technically, I actually got it correct for the first time. So this moves you to the right to the hashtag, and so now this takes you up to this point in the string. Now I'm going to change it a little bit from what I presented last time, because I want to give an improved variant of it. Notice that we've already taken care of the case here where m is equal to 0. So if we're going this way, it must be the case that m is equal to 1. So there must be at least 1a, 1b, and 1a. Well, hey, we already marked one of our a's. There may be other a's after that. So what I'm going to do is I'm also going to mark the first b in this sequence as well. So I'm going to take care of this one sweep at the same time. This is going to become a really nice trick that's going to build up for us later. So what we're going to have here is we'll see a b, and we'll take that b and we'll mark it with b dot, and we'll move right. Let me finish off this whole phase, and then I'll show you how we finish off this sequence. Now, from here, what we do is we have a loop, and we loop here on b's, replacing them with b's, and moving right. Eventually, we'll see a hashtag. We'll replace that with a hashtag, and we'll move right. Now we're going to do the same thing. We're going to mark the first A up there as well. So we'll see an A. We're going to replace that with an A dot, and we're going to move right. Now, what we're going to do is we're going to keep on making sure we see A's. So for every A, we're going to replace it with an A and move right. And then eventually, we'll see a U. We'll replace that with a U and we'll move left. So, what do we do now? Well,
Rewind the tape.
now we need to rewind back to the very beginning. So we want to go back to that very first A. Well, how do we get back there? Well, we first rewind all the way back on A's, go to A, go to left, A dot goes to A dot, goes to left.
And last space goes to space is a left, right?
Yes. Because you get to the end of the tape and you're like, rewind. Then eventually we'll see a hashtag, because we've now rewound past that phase. Oops. Rewound past there. Now we get to the hashtag, then we need to rewind there and we need to rewind each of those components individually. So we'll see a hashtag, which goes to hashtag left. I'm running out. Now I have another rewind loop here, where I say B goes to left, B dot goes to B dot goes to left. Now, hashtag goes to hashtag left. Now we get to the final rewind. The final rewind we want to do is we actually don't want to skip over all the A dots now. Now we actually want to get to the first undotted A. So we have a loop here that goes A, left, and then eventually, and we'll show what this actually connects to, on A dot, replace that with A dot, and go right. We're done with phase one,
With checking of.
with checking the format. Let's go through an example of this. Sound good?
So just really quick before we go on.
Mhm.
Last class,
Mhm.
whenever we set this up,
Mhm.
we didn't have these transitions. So like after the first hashtag.
Yeah.
And then it goes to B dot.
Right.
So should we just scrap the last example?
Other example will work, but you need to modify it slightly. This change, even this longer here, will be an improvement in a few minutes. Either approach will work, but
But you're teaching us this approach.
I
So
mean,
the other one,
the other one is a legitimate way of just checking the thing, but I realized as I was going through it after class that there was an improved way to do it. And so I decided I'm teaching you guys the better way. And it's better because it makes the more complicated part of it easier. It makes the basic part harder, but it makes the more complicated part easier. And so,
Is the hash never going to the cell loop because it's only have one?
right, there's only one.
It's not like
Yeah, there's only one. There's only two hashtags in the whole thing. So let's see how it processes the string A hashtag B hashtag A space. Starts off here, marks it with an A. Scrolls to the right to the hashtag. Goes to the hashtag. We're now in this location. Sees the first B, marks the B. Forwards to the next hashtag, puts it into this location. We're now at the A, marks the A, comes down here, goes to the right through all the A's, then sees space. The space, once it hits that, goes back to the left. Now we rewind back to the hashtag, and that's what this sequence does. Now we're at the hashtag, we go left through our B's. Then, as soon as we go left through our B's, we go left through the hashtag again. Now we rewind to the A's until we see the A dot. As soon as we see the A dot, we now go forward one character. So our tape head is right there in that state. So much work for so little reward. Does this make sense?
Yeah.
Everyone's in the tugboat?
So you just go through this exact same thing over and over again until you.
A similar process, yeah. And so what we want to do now is, now that we're right here, what we want to do is we want to go mark that first A, then scroll forward to the hashtag, then find the first unmarked B, mark that, then scroll forward, find the first unmarked A, mark that, until we've marked all of our A's and B's. And so each time we're marking one at a time.
so then, if there were, say there were like 4 A's in the first part,
Mhm.
whenever it scrolls back, if all of the 3 A's are marked, and then all of the second B's are marked,
Mhm.
and then not all of the first A's are marked, then it's incorrect and it goes to a reject state.
Yeah, yeah. Yep.
So basically this just goes through it and validates that each character it encounters is what it should be.
This part right now, it's doing two things for us. One is it's setting us up for success later by already counting that we have, if there's at least one of each of those. Because we know that we should be in that state because we've already done the one where there could be 0. So it validates that for us. In addition to that, it also validates that it's all A's, hashtag all B's, hashtag all A's, space. So we know from this point forward it is in proper order. So, we're now back at the very beginning here, which is the space right after that. What are the possibilities of what it could be? There's two.
An A or a hashtag.
Right, it could be an A or a hashtag. I'm going to draw these back over here so we have more room. So, let's do the hashtag one because the hashtag is going to be our success story. So, if we see a hashtag, we replace it with a hashtag and we go right. We are now in a condition where we have run out of unmarked A's. And so what we want to do is we want to validate that there are no more unmarked B's or additional A's. So we come through here and we loop on B dot, replace that with B dot, and that goes right. Then we see a hashtag. The hashtag we go right, and then we have another loop here that says A dot, go right. Then, if we see a space, we go replace it with a space and go right, and that's accept. So, we would be in this condition if we were to have the string A, hashtag B, hashtag A. Because we come through here, we see a dot, we put a dot on the A, put it on the B, put a dot on the A, rewind hashtag, rewind B dot, rewind A dot, go to the first space to the right of an A dot, hey, womp. That's a hashtag. Now we're at a hashtag, we want to scroll through. Hey, all of our B's have been marked. Yes, skip that pass. See a hashtag, see an A, see all of our unmarked A's, yay, eventually we get to the end space, good to go. Now, we often ignore reject states. It might be worthwhile to be explicit about 2 reject states here, which is that if we see a B, then we replace it with a B and reject. Or move right, doesn't matter. Or similarly, if we see an A, we replace it with an A and go right. Because if we see an unmarked B while we're cycling through the B's, that means we fail. If we see an unmarked A while we're cycling through the A's, then we fail. For example, we would want A, B, B, A to fail. We'd be in the state of we mark the A, mark the B, mark the A, come back to the A, all the A's been marked, hashtag, oh, there's a B dot that's been marked, hey, there's an unmarked B, we fail at this point as soon as we read this input.
Do we need the explicit fail-safe there?
It might be worthwhile. It might help you in just writing it out and making sure you're clear on it. You don't, again, I'll accept it if you don't have it, but just for your own sense of being, it might be an easier thing to do.
So these, so by the time you get to that area, all of the A's should be A dot and all the B's should be B dot?
Right. And if they're not, that means you have a mismatch somewhere.
Oh, okay.
So that's just one of the 2 options. That's the one where you see the hashtag immediately after the A dot. we have another option here. That other option is that when we rewound the tape, we had an additional A. So the other option could be like this one, where we saw an A right after our dot. So in that case, A, we want to replace that with A dot. And go right. So in this one, we want to replace that A with an A dot, and now mark off that one, and that one. Okay?
So, one thing is, how do they all get marked A dot and B dot when it only,
We're not done with it yet, so
oh,
we're finishing that. We're finishing that part right now.
okay.
So we see that A dot. Now what we need to do is we need to now cycle forward to the next unmarked B. So what we'll do here, we can actually cheat a little bit because we already know the things in the proper order. So we'll make our self loop. Here it will go through every A, replace it with an A, and go right. Hashtag, it'll replace it with a hashtag, and go right. And actually every B dot, it will replace with a B dot, and go right. Eventually we'll see a B. And that B will now replace with a B dot, and then we'll go right. So now we've now put the dot on that one. And what we want to do now is we need to find the next unmarked A and dot that. So we do another self loop here. Every B, replace with a B, go right. Every hashtag, replace with a hashtag, go right. Every A dot, replace with an A dot, and go right. And then eventually we'll see an A, replace that with an A dot, and now go left. And coolly enough, now we just rewind at the very beginning. How can we rewind it to the very beginning?
So, go back.
This is why I changed the modification to go through the first marking as opposed to making them asymmetric. Makes it so the part where you're actually counting the number of A's is actually much shorter. I mean, 2 states. As opposed to, which would have been actually substantially more. I don't know how many states it would have been. I'm just drawing that for clarification, please. Is it simple, right?
So, where's the third step?
You don't need a third accept. You're re-leveraging this previous accept.
Okay.
So let's go through it. Let's go through it.
Oh, so then whenever it sees an A dot and then a hashtag, it goes to that.
So let's go through this whole string AAA, BBB, AAA one time so we can actually see how the whole thing works. Get it kaboom. Alright. So start off, we mark our A. We now scroll forward to our hashtag, and that takes us to that location. See a B, mark the B. Scroll forward via that to our hashtag, see our first A, mark the A. Scroll forward until we see the space. Once we see the space, we go back. Now we rewind to the hashtag. Changing my arms. We rewind to the hashtag. Now we rewind to the B's to the next hashtag. We rewind all the way back to the first marked A. As soon as we see the first marked A, we go forward a character. And if that character that we're looking at now is an A, which is this case, we mark it. That's this transition. Now we scroll forward through our A's, hashtags, and our unmarked A's, our hashtags, and our marked B's to get to the first unmarked B. We follow that transition, mark it. We now scroll forward past our B's, hashtags, and marked A's to our first unmarked A. Mark it. Now we don't need to even go beyond this because we've already validated that the format is properly. So we can now rewind the whole thing, come back to our rewind state that we made earlier, and that will take us to the hashtag, to the first marked A. State after is an A. Mark it, scroll to the next B, mark it, scroll to the next A, mark it, rewind, come back up here, rewind to the hashtag, rewind to the B, to the next hashtag, rewind to the first marked A. That we see a hashtag as our next character. That means we are done marking A's, so it means that every other A should be marked at this point. So, we come down to here, we should see marked B's. Hey, we see all marked B's. Hashtag. We should see all marked A's. We see all marked A's. We see a space. We're good to go. It's magic dot Turing machine.
Tried that.
Does this make sense? I mean, don't get me wrong, it's kind of a pain in the ass.
They're gonna be on the test.
Yeah. I will give you something about this long on the test. 2-hour test. Guess what a main question on the test is going to be?
That one.
This one.
Not this specifically, but it'll be something similar to this.
So is it basically going to be building these PDAs and
A large part of the test is going to be that, yeah.
just those constructions?
Yeah, and that's there's a lot more to theory, but in a 3-week class, what I have time to focus on is the mechanics of building these things, rather than the large underpinnings. So that's what I've chosen to focus on. So you have 3 things you know really in depth, and the philosophical implications of this we haven't really talked that much about. We are right now, so don't worry about it. But it's hard for me to ask questions on philosophical implications of things, because it's kind of you know them and you can regurgitate them or not. And unlike normal philosophy, there's a right and wrong answer here.
This is philosophy.
Is it? Okay, does everyone feel like if I gave you something about this complicated, you could do it on the test?
Could we do possibly like other example?
Yeah, I'll give you guys. I don't because the homework assignment because I know there's no way I'd have you have it graded back to you. I'll write up another one of these, and I'll post it on the Moodles.
And then will we have solutions to the homework that we currently have?
Yeah, I'll post those. I'll post all the solutions online. Yeah.
Okay.
Yeah. So, because it seems like something you should have.
Yeah.
Yeah. It does seem like a worthwhile activity. So let's talk a little bit about the philosophical implications of a Turing machine. So as I mentioned before, one of the big things about a Turing machine is that it can, and we're going to state this without proof, but a Turing machine can be built to represent any bit of pseudocode. So if you were to write pseudocode, I can create a Turing machine that will do the same thing for you. This is called the Church-Turing thesis, and it's the reason why Turing machines are so popular. Now, one of the things, the implication of this is that, how many people remember Gale from any one of my classes?
Oh, the guy did Principia math. Or no,
No, this is the guy who looked like a vampire. You guys might remember that reference from my intro class. So, Gale, which is a great name to throw out there if you want to look pretentious, Gödel he was what?
Oh, the math dude.
Yeah. He was the guy who proved essentially that any way, if you can define math such that it can represent the natural numbers, then any mathematical system in which you create will either be incomplete or inconsistent. Gödel.
Other people pronounce it Goodell.
They could if they're pronouncing it.
Okay, so then it's okay. Then yeah.
Other people pronounce it Gödel as well. I can spell it.
That was a yeah. I've never heard it pronounced that. With the
Yeah, there is an umlaut there. I got yelled at for someone for calling him Gödel. Yeah. They're like, he's not a character from The Hobbit. I'm like, he looks like one. He looks like a vampire. Like,
It's crazy as well.
yeah, he was a crazy man. He was really a crazy man. But anyways, so he proved that any mathematical system that can define anything sufficiently interesting, and he defines sufficiently interesting as can do addition and multiplication on the natural numbers, seems like a good low bar, is either going to be incomplete or inconsistent. This means that if you can create theories about this language which cannot be proved at all. And it comes down to this idea that he managed to state formally that if you can do addition and multiplication, you can always create a theorem that says this theorem is unprovable. So you know if you can't prove it, then you know that theorem is true. But if you can prove it, then you've now proven your system is inconsistent, because you're now proving something which is wrong. That is a high-level overview of it. It's actually it's a great Star Trek episode. But the thing is that it turns out that you can mathematically prove that any system that can do addition and multiplication always has a theory in it that is the equivalent of this theorem is unprovable. And his work is formally defining that process for any axiomatic basis that can do addition and multiplication, that this theorem comes hand in hand with that. It turns out you need addition and multiplication. Addition is not sufficient. You can actually prove that addition systems can be complete and consistent. Furthermore, he also proved that we will not know if any axiom system we create is inconsistent, and that is unprovable. If we can ever know if the system that we've created for a mathematical basis system will never create a contradiction. People have used this as jokingly as the proof of the existence of both God and Satan, because the idea is that we know set theory works. And that's what we use now. It's called the ZFC set theory. There's other axiom bases out there, but ZFC, I can't pronounce the guys' names. ZFC is the standard basis that math uses right now. There's other ones out there, just like there's non-Euclidean geometries. But this is what we use. We know it works. We know addition and multiplication work. I don't have doubts that they will work. And so the joke is that we know God exists because addition and multiplication clearly work, and we know the devil exists because we can't ever prove that they do. This is how mathematicians reason about religion, I guess. The reason why this comes up when we're talking about Turing machines is because Turing machines can represent any bit of pseudocode. Well, what is math really, man? Math can be solved by a computer. If you give me a theorem and a proof, I can create a computer that will validate that proof. If I can't, then you have not written a good theorem or a good proof. As a result, all of math can be viewed as a subset of computer science, and vice versa, Jay Lee. And so that they are two sides of the same coin. As a result of this, guess what can do addition and multiplication? Turing machines. Since Turing machines can do addition and multiplication, they are subject to the same constraints that Gödel proved. The question is, how does it come up? Because when you're talking about math, you don't care about the sequence of steps to get there. Now that you do when you're writing them, but largely mathematics is not concerned with the process for building something. It is concerned with it is an existential proof that things just are. I can have a set of 4 numbers. I haven't built that set of 4 numbers. Just A is a set of 4 numbers. Computer science and Turing machines, on the other hand, are concerned with this process of processing, of building and constructing things. So what is the equivalent of Gödel's proof in computer science? That is what's called the halting problem. The halting problem, at a high level, states that we can never tell in advance when another Turing machine will halt without actually running through it. So remember how I mentioned that Turing machines have 3 different states associated with them. They have accepted, reject, and processing. Some programs will run forever. I'm sure you've written these in intro. Yeah. Well, true, do. Yeah. Break. So you've written programs that run forever. Some programs can be analyzed and figured out fairly easy if they can be run forever. If you see a while true loop in there, chances are it's going to be run forever. But there exist problems out there that we can never tell if they will run forever. It just looks like they're going for a really long time. It always looks like, we're almost there. For example, if you had a program that was calculated, so suppose you had one program that calculated every digit of pi. And then you had another program that calculated the first 10,000 bits of pi. And you were just looking at the output of these two. Would you know the difference between the output up until point 10,000? It would look like they were the same program. So if you were just looking at the output, you wouldn't necessarily be able to tell which one was going to terminate and which one was going to run forever.
Wouldn't the infinite one eventually just crash your box?
No. Infinite memory, man.
Oh, right.
Man, we got all the memory we need.
Okay, so you're running it running it on a computer
On a
that's in
Turing
the future
machine.
from space.
No, on a Turing machine.
Okay.
Pen and paper. We have not yet harnessed this. This was a major topic last class. When we fully realize pen and paper, then we'll be fine. Now, but yeah, so you assume that it can run forever. Now, there's a difference. It turns out you can actually still have these are called undecidable problems on linear bounded automata or computers as well. But pi is that example is not a real. It's more of an illustrative purpose. It's not a real program that you can differentiate because you could analyze the code on there and be like, will it run forever? No, it's going to run 10,000 times. Just look at the for loop and count it there. But there are programs out there that will run forever, and we don't necessarily know what they are. And that's the other kickers. We don't know what those programs are. Some programs we can do. Now, are any programs you're going to run forever without you being able to figure it out? No, we won't run into that. But just like you don't accidentally write up a theory. This theory is unprovable. It exists, and there are programs out there that will never halt, and it's a real limitation of computers. But at the same time, you are not going to run into this on a daily basis. So the way we show this is true is we create a Turing machine. We're talking about a language, and that language is ATM. ATM is the language comprised of Turing machines and words, where the word is accepted by the Turing machine. So, if I were looking at it, this could be my M. This would be my W. So, this machine with this word would be in that language. Okay? On the other hand, that would not be in there. So it's a machine word combo. What we do here is rather than talking about it halting at some point, we talk about decidability. And remember, decidability means that every string will be either accepted or rejected. So if you give me a machine and a word, can I decide if that word will be accepted by that machine? The answer is no. Not all the time. Sometimes. The way we do this is a proof by contradiction. We assume that it is decidable. If ATM is decidable, then there exists a Turing machine which will take as an input a machine and a word. And it will spit out true at some point. I don't care how long it takes. It could take a jillion years if it will happen. It will spit out true if that machine accepts that word. And it'll spit out false otherwise. So it'll spit out false if the machine would spin forever on it, or it would spit out false if it would reject it. If ATM is decidable, then that machine must exist. So what we do is we call that machine H. We don't talk about how to make this Turing machine, it's just it must exist. Proof by contradictions. So it takes an input, accepts if M accepts W, rejects if it does not accept, which again could be processing or actually rejecting. Now what we're going to do is we're going to make a crazy alternate machine that I like to call the asshole machine, or D, because we're being recorded. Yeah, what D will do is D will take as an input a Turing machine. D will then run this machine H on the Turing machine that was an input, and itself as the input. It will then output the opposite. You got to memorize this proof, so.
Yeah,
I mean, my theory class memorize this proof word for word. Then we output the opposite of H. It's the only thing I make them memorize verbatim. What's happening? Okay, so I want to talk about this for 1 second. You can take an encoding of this. So I could take this machine and I could feed it to itself. Suppose I were to turn this into a string of 0 or A's and B's and feed it into itself. Most likely it's going to reject it. But there are other machines out there that take Turing machines as an input and will accept them. So for example, suppose I were to create a Turing machine that would validate, is what I'm being given a proper Turing machine? That seems like a legitimate Turing machine to make. So as an input, it takes Turing machines. D is one of these. It takes as an input a Turing machine. We're going to go over this again.
Well, it just seems like that would take literally forever.
And that's what ends. Well, it takes a long time. It doesn't take literally forever, but it takes really almost forever. So what ends up happening is we run H on there, and then we just output the opposite of whatever H does. So if H says that that this machine accepts itself as an input, then we reject. If H says this machine rejects itself as an input, then we accept. Well, then what happens if we run D on itself? This is exactly the same thing as I talked about earlier, basically saying this statement is unprovable. If D says D will accept itself as an input, then it rejects, but that just says it should accept, and vice versa. We're going to go through this again on Friday, because I know we were 1 minute over already, and this is a somewhat important proof in theory. By somewhat, I mean the most important proof in computer science. So,
With us memorizing.
yeah, it's the only proof I've ever made people memorize.
So basically, you're saying that you're proving it's undecidable by showing that